this topic is one that is super important, and you're hearing more and more about it these days. There is an arsenic issue in the state of Maine and New Hampshire. There's a lot of work to be done about, understanding where the problems are and what the frequency of testing should be going on in our wells and all of that. And some of you know me, I'm Jane Disney, and I've been running this Science Education Partnership Award project and engaging kids and teachers in monitoring their wells for arsenic. And we have been all around the state of Maine and New Hampshire over the last couple of years, and will continue over the coming 3 years. And in this project, we're just finding a higher incidence of wells exceeding this maximal limit that is set by the EPA more frequently than we thought that we would. And so I feel really fortunate that Sarah Hall, who's going to be our speaker tonight, is right down the road at College of the Atlantic. She's a geomorphologist and understands the bedrock and the geology that explains this incidence of arsenic in our well water. And this is totally not my area, so it's such an interesting merging of work that we're doing. And she has all of her College of the Atlantic students who are very interested in the geology of the area and in water quality. In addition to the work that she's been doing to engage her students with our high school students and teachers and looking at this arsenic problem around the area, she's also working with Friends of Acadia and Acadia National Park, looking at different issues in watersheds around the island. She's going to be talking to you more about that work, but she's got her eye on the water and how it's really influenced by the bedrock in which it's flowing. She has an interesting background. She went to Hamilton College in New York State, and then off to the University of California at Santa Cruz for her Ph.D. work. My sister is living in Santa Cruz, so I can picture right where she was when she was studying, and talk about interesting geology. She spent time up at McGill University doing work before she arrived at College of the Atlantic, and everywhere she's gone, it's always been about the geology. So I actually got through all my years of training with never taking an earth science course. I don't know how it was allowed, but I've had this wonderful short course in geology all year long, and so now you're about to have it as well. She is the professor of Earth Science and the Ann T. and Robert M. Bass Chair of Earth Systems and GeoSciences at the College of the Atlantic. So obviously a big wig over there. Yeah. And so I can't wait for her to tell you all about her work. And then after she's done, I'll tell you more about these science cafes and some of the upcoming events that are going to be happening throughout the winter and the spring. All right, so without further ado, thanks.
Thank you all for coming tonight. It's cold and potentially slippery, so thanks for taking the chance and coming out. And thanks, Jane, for that introduction. I'm just down the road at COA, and I'm the only geologist there, so it's great. I get to dabble in stuff that has to do with rocks and with water and climate change. And landscapes. But a few years ago, I heard that here in the community lab at MDI Biolab, they were doing this project with arsenic in groundwater. And they had written some grants. Jane and Bruce Stanton here, these two are the PIs on grants, first an EPA grant and now an NIH grant, to test people's water through the public school system, and also use it as a platform for data literacy, helping students learn how to understand data and helping teachers teach how to understand data. And I thought, well, awesome, they have an infrastructure, and I can maybe just get my students involved too and expand the sampling by offering this, this army of COA students to go out in the community and collect some additional samples so that we can ask some questions about the spatial patterns, if there are any, of groundwater chemistry. And of course, if this is not a new idea, lots of people have already said, yeah, we know the arsenic's coming from the rocks, and I'll show you some of that previous work, but I really wanted to take a look in this community at MDI, given that we have some local rocks of interest, and this is a big tourist destination because of the beautiful, iconic geology and landscapes that we have here. So these are some of the folks I've worked with on this project. I've already mentioned the community lab folks and Bruce Stanton. at Dartmouth College. The high school teachers I've worked with in the last 2 years, Ruth Pullen, and I'm working with Hannah Peturgil this year, and their students. And then lots of COA students have helped with this project, but one in particular, Gabby Morose, did an independent study project with me on this last year and has continued to work on it. She's presented at a few conferences, and she made a lot of the maps that you're going to see in the COA GIS lab. So big shout out to Gabby, who is sick today and couldn't come. But anyway, this is the grant that Jane mentioned is current right now, the NIH grant, and there's these different components to the grant, and one that I'm involved in with them is working with high school teachers and students to test their water at their home. And the work that I've included to this sort of as a side add-on to this project is work with COA undergrads, where we've scheduled multiple sampling events in the northern part of MDI since about December 2016. We've had about 3 or 4 sampling events targeting this one area, and many students have helped with that in different ways. So I'm going to tell you mostly about that today. So we have arsenic in our groundwater, among some other things, and we have the rocks mainly to thank for this. This is a map, a geologic map, shown on the right here in a paper by Peters et al. From 2008. And, oh, sorry, I don't know if you see. And these rocks are, all the gray rocks that are here, the dark gray rocks, are what are called meta-sedimentary rocks. By the end of this talk, I think you'll know what a meta-sedimentary rock is. But it was a rock deposited in an ocean, a sedimentary rock that became metamorphosed. And you can see they stretch all the way from down in New Jersey, through New England, all the way up through Maine, and they continue. Rocks don't actually pay attention to political boundaries, so they continue into Canada. And you can see that there's also these gray stippled areas. Those are igneous rocks like granite, like what make up our island. So this whole region is mostly meta-sedimentary rocks and igneous rocks. And that same footprint is where we also see the high arsenic groundwater. Not every well has high arsenic. Some do, some don't. So we know this region is known for this, and so this is not a new. I'm not saying something wildly new here. I'm just kind of going to take a closer look at our area. So. Thank you, Anna, for this table. I use it all the time, super useful, where she has got together some of the stats here on why this is also important for our area, not just our rocks, but being a rural state, a lot of people rely on well water for their drinking water, half the state, in fact. And of those, the wells of those 56%, we see that 10% of them have elevated arsenic, if we know it. I mean, if they've been tested. It turns out that many of them have not even been tested for arsenic. So, I mean, it's relevant to talk about, since so many people in our state, and also New Hampshire, some of these other states may have arsenic in their waters as well. Depending on how many people rely on wells, that might be a concern for people to talk about there as well. So it's relevant for that reason. And another thing is that, arsenic is a toxin. It's a toxin at any level, really, although especially, we've been talking about lately how chronic exposure to even low doses can add up. And so this is a recent study that shows that there's elevated bladder cancer in New England, and these maps are all pretty much showing the same thing. These are with white males or white females, so they're just telling you the population they studied at different periods of time, 1950 to 1979 for the top two, 1980 to 2004, and you can see in all cases New England and Maine is red, meaning it has the highest risk of bladder cancer compared nationwide, and it's I guess it's maybe a little redder, I don't know, but maybe this is continuing to be a problem as we have more and more wells drilled. This graph is from the same paper, and it shows through time the number of drilled wells. And you can see, I mean, since the 40s, it's been increasing as people are relying less and less on dug wells, which has been reduced. I mean, people are moving into rural areas like here, where we don't have public water supplies that extend to the entire population. Something like 80% of Hancock County is on well water. This dotted line shows another source of arsenic that's not bedrock, and it's not the rocks. It's actually was agricultural. It was in agricultural pesticide or chemicals, and that has been declining because it's not used so much anymore. But some of that can reside in soils And so there may be some concern for that in dug wells, in the shallower wells. So dug well, drilled well, you get to worry about arsenic maybe either way. But there's some good news. There's lots of work that's being done on it. It's being talked about, and there's options for mitigation. Just to say that, you know, there's many people working on this, including geologists, like at the U.S. Geological Survey, who study groundwater. This is a paper from 2002 that specifically looked at our groundwater here on MDI. How much water is there? When is it recharged? What are the flow rates in different parts of the island? And this one more recently is actually looking at arsenic concentrations in Maine by town, and that was published in 2010. So there's some work being done, but that doesn't necessarily mean that people are using the data and implementing these mitigation systems. So in fact, there's a couple other studies that focus more on, well, how is it getting from the rock into the water? So this is a geochemical study to explain how it's moving. And other studies that are like social science, behavior and risk. How do people perceive the risk when they get these results back from the state? Okay, so I got a number 8. What does that mean? And so there's people studying that aspect too. So in this particular study, which was of central Maine, sort of near Augusta, 27% of well owners in this study area did not act upon receiving their results, indicating that they had high levels of arsenic. And they cited lack of concern and perceived cost for reasons not to mitigate. And so I think there's still some conversations to be had about maybe there are cost-effective ways to mitigate, and when is it that you really should consider drinking different water. Okay, so back to the rocks. Here is a simplified geologic map of the state of Maine. It's so beautiful and colorful. These stripes that are northeast, southwest of blue, green, gray, orange, all of these rocks that are oriented this way are the metasedimentary rocks of the state. And in the middle here is the Great Maine Slate Belt. Slate is a type of metasedimentary rock. Our local metasediment is the Ellsworth schist, which is shown in orange on here. The other thing on this map that you can see are these blobs that are pink all throughout, and those are the igneous rocks, the granites. The Sebago granite, that's a big one, and the MDI granites, bright pink right here. So the short story geologically in Maine is metasedimentary rocks intruded by younger granites. And so I want to take you through a little bit of that story because that's the part I get really jazzed about and I like telling my students about. I mean, the Earth is really old and we should, just at least spend 5 minutes on things that happened 400 million years ago. And this story applies not just to Maine, but to much of the Appalachians, and at least in the Northeast. So I've turned the map on the side. Here's the state of Maine, and this is like Massachusetts, Cape Cod, and up through Nova Scotia. And these terrains, so now the rocks are not exact rock types, but rather correlative rocks that are pretty similar in time and type. So you can see this Great Maine Slate Belt and the metasediments continues all the way up to the north. Rocks, like I said, don't care about political boundaries. And these names here are given to describe these different terrains, and this terrain in the middle is called Ganderia. That will come back up. So the story of Maine involves plate tectonics. The surface of the Earth and the configuration of the continents and oceans has not always been how it is today. It's constantly changing, although kind of slowly, like the rate of fingernail growth. That's about how fast plates move around on the surface of the Earth. Well, 450 million years ago, and I picked that date because that's about the age of a lot of our rocks, the Earth looked like this. And these are both the same view, except for one is sort of a digital description with some labels, and this one looks more like what Google Earth looks like. I love these maps. They come from Ron Blakey's lab, and they've been making a lot that really use the same like visual codes and symbols that we see in a lot of other maps. So it's really quite helpful. You can see where mountains are, like there's the Appalachians. So this continent is called Laurentia, but you can think of it as proto-North America. It's what will become North America. And there's this little group of microcontinents, and those are like Indonesia and Japan and off of Asia, up to the east of Asia. There's microcontinents, little tiny like strings of islands, and these are named Avalon, Ganderia, Maguma, and these terrains will eventually accrete to the side of North America. So the Appalachian Mountains were built through the accretion of little terrains through time. and they're moving.
Could you use your pointer up top, because we can't see it on the bottom.
Oh, I'm sorry. Okay, yes, thank you. Good point. Okay, so here's North America, or what will become North America, and these are the little micro continents that are going to accrete onto the side of North America over the next few tens to hundreds of millions of years. So one way we can think about time is to look at it in little steps in images like this that are called cross sections. This is like if you took a slice through the Earth and looked at it from the side. It's like a profile. So 1 billion years ago, we had a supercontinent called Rodinia in this space, and it was a huge continent, and that broke up and the continents moved away again by about 600 million years. By 500 million years ago, here we have the edge of Laurentia, the east coast of what will become North America, and some microcontinents like Gandiria or Abylonia that are off away in the ocean. And they are moving towards Laurentia along this area called a subduction zone, which is where one plate goes underneath the other. And in that moment, ocean basins can get closed. And I say moment, and it's millions of years, so I don't know, not really a moment like that, but what makes a moment? So by 450 million years ago, this microcontinent has been attached to Laurentia, and that formed in the Tectonic orogeny. If you drive down from Boston across New York State, you go over the Tectonic Parkway, and you're in that mountain belt that was formed here when that little terrain accreted. Here's another piece of a microcontinent that moves also across the ocean through time and accretes onto North America. So this ocean basin here is where clay, silt, sand is being deposited. Just like right now, if you went with Diver Ed out in his boat and went to see what's at the bottom of Frenchman Bay, it's clay, kind of like fine grained stuff. Well, as this ocean closed, all that clay and stuff got kind of folded and stuck onto the state, and that became the Great Main Slate Belt. It was the bottom of the ocean, and now it's accreted on the side of North America. Eventually, Africa collides with North America. We have huge mountains like the Himalayan mountains today, where India is crashing into Asia. And we have the supercontinent Pangaea at that time, about 270 million years ago. That's where the dinosaurs lived. Then Pangaea started breaking up. It was kind of a long breakup for about 50 million years or so. In fact, it's still going on today, where at present we have the edge of North America and into the Atlantic Ocean, and so that's what's shown on this lowest one. I'm sorry, you can't see it back there. I didn't realize. Put stuff up higher. So 450 million years ago is kind of an important time here because there's lots of rocks that are forming about that time. Actually, Ellsworth schist is 500, and the granites are about 420. So now I'm just going to zoom in on MDI and tell you how this plate tectonic story I just told you relates to us right here. So this is the geologic map of Mount Desert Island. It was made in 1988 by Gilman and Chapman, and has been since remapped by Dwayne Braun, and he has this beautiful new map. It just came out, so I really need to update my slides. I don't even have a print copy yet, but it's beautiful. And I highly recommend. He and Ruth, his wife, made the Guide to the Geology of MDI, a great book. So the Ellsworth schist is shown in brown on this map, and here's a little picture of it. It's all folded up like mixed up Play-Doh. It's kind of green and shiny, and you can see it at Hadley Point. And this Ellsworth schist was originally deposited in an ocean basin as clay, silt, sand, and it got crunched up and deformed through those mountain building events that I described. You can, so you can see it here at Hadley Point, also at Seal Cove. I think I have a picture. Yeah, here we go. At Seal Cove, you can see some really nice folds in here and some little quartz boudins. Beautiful. So the Ellsworth schist is our local sulfide-rich rock. It's one of these metasediments that have a lot of sulfide minerals that can harbor some metals, including arsenic, and then release those metals when they are exposed to hydrothermal fluids, hot fluids. And so what's the source of that heat? Stay tuned, it's coming in a second. So another metasediment we have is the Bar Harbor Formation, which is on the east side of the island. So the island is flanked by metasedimentary rocks. The Bar Harbor Formation is much younger, like 50 million years younger than the Ellsworth schist, and it was formed about 465 million years ago, also in an ocean basin as that ocean was closing. Silt, clay, and ash from nearby volcanoes combine to make this nice layered rock. It's not as mixed up and folded and foliated and shiny schistose, we say, as the elsewhere schist. But where we see it at the Bar Harbor shore path, it may be tilted just a little bit because it did go through some mountain building, but nothing as extreme as the elsewhere schist that's much more deformed, we say, or foliated. So this is at the Bar Harbor shore path, and you can see that nice, this is like what everybody takes a picture here by this nice sea stack. It's beautiful. So then we have the source of heat. 420 million years ago, the big event on our island, the granite forms, and not just the granite, but it turns out all these pink, reds, oranges, yellow, beige, purple, all those rocks are igneous rocks. Most of them formed in a magma chamber underneath a supervolcano. A magma chamber that, here's it, you can just look at this picture, people can't see below. There's a volcano on top and underneath a magma chamber, a room filled with magma. I always ask my students, like, what does a magma chamber look like? Nobody knows. We just draw it and we say, this is what a magma chamber looks like. But it's a bunch of hot liquid rock that cools slowly over time to form granite. And that rock is in contact with the metasedimentary rocks that were there before, the Ellsworth Schist and the Bar Harbor Formation. So this magma is like 700 to 900 degrees Celsius. It's pretty darn hot. So it's really baking the rocks right next to it. Those Bar Harbor Formation, Ellsworth Schist, they get a little bit heated and even metamorphosed a bit more. The other thing that heat does is it heats up any of the water around. We have lots of groundwater down there in our cracked up rocks, and this intrusion would have heated that water up. And hot water does a pretty good job of leaching metals out of rocks. So that's one step in how the arsenic got from the rocks into the water, and then it will eventually get to your well, but we'll get to that part. But so this was important, that we have metasediments and igneous is part of the recipe for getting metals into groundwater. And then here's just the Cadillac Mountain granite. That's the yellow one, nice and pretty pink, with big crystals. Okay, so back to the state of Maine. I just told you a story that included mountain building. If we look at the slice right through Maine, the cross-section, people in the back can't see it, but here it is along the bottom, and what you can see is this great Maine slate belt is all folded up because it got crunched between two continents that were coming together. I added a red dotted line on here, which is the position of something called the Noren Vega fault. It's the place where the boundary between where one microcontinent collided with the edge of proto-North America. It's like the boundary. And it's a fault zone, and when you drive to Bangor from here, you cross it. And it's like everything I can do to stay on the road when I'm like looking at the wrong stuff. I've seen it hundreds of times, and I still can't help but look at it. So I put that here, and on other maps for reference, you can see it in the cross-section as well. And it divides rocks of one microcontinent from rocks of other microcontinents. So they're a little bit different genetically. They all kind of have a lot of metal in them. Sulfides in them. Okay, so back to the water. Again, here's the high arsenic area. If we now look at this same picture I've shown you, turns out all geologists who talk about the Northeast use this figure because it's classic, it's in all the textbooks. Peters used it as well, and they highlighted where the arsenic-bearing sediments were coming from. So here is one of those microcontinents. There's erosion going on, just like today. It rains, sediments work their way from the top of Cadillac down into the ocean, and it goes into the ocean and they form sediments. Eventually, those get slammed up on the side of North America and form the Great Main Slate Belt or the Ellsworth Schist. So that's how this fits into the story of plate tectonics. Now, what about our groundwater? Well, here's that geologic map, and the island of MDI is in the box, and I did that on these two maps as well. These maps are from the Maine Center for Disease Control. You can, it's like a dynamic user interface where you can map things that you're interested in. So I highly encourage you to check it out at the Maine CDC. But this map in the middle is showing you the maximum arsenic value in micrograms per liter, parts per billion by town in Maine. So the higher, the redder the colors, the higher the values. And you see next to like a Blue Hill and just off to the west of MDI, there's a high area, and also in Portland, and kind of like a stripe. You can see some stripes in here. So those are some high arsenic areas. And I also included uranium because I want uranium to start entering the conversation of things to pay attention to in groundwater. And there's not as much of a, I mean, I guess you can see that there's some high values, but you don't see lines, they're kind of dispersed throughout, but we'll come back to that. So, so here's the red dotted line for where that fault is. I thought I'd just show you that. And you can see it's sort of a similar trend to this line of high arsenic areas. So now, for the next few slides, I'm going to keep this map on the left, and it's the percent of homes with private well water by county. So the higher the brighter the red, the higher the number. So coastal Maine has a much higher percentage of homes with private well water than other parts of Maine. I mean, down East Maine, it like lights right up. And then next to it is the number of wells with test results for arsenic by town. And the most of them are in the south. So not where there's the highest percentage of wells by county, but they're mostly in the southern area. And you know, there's also a bias, like how many wells are there, how many people are there that are sampling, but you know, still notable. And the white squares here are places where there are no data. There's no data from places where people don't have wells or they haven't sampled their wells. Now this is showing the percent of wells that exceed the guidelines of 10 parts per billion, the limit. So not just who's tested, but where are they exceeded? And again, you can see kind of a stripe here and a stripe here, maybe a little bit of a stripe there. So maybe we can start to see some patterns a little bit. But again, these are by town, political boundary, rocks don't care about those. So it's a little bit hard to look for spatial patterns with these kinds of maps. Okay, I went backwards. Okay, so here's those maps again. Now we're going to zoom in on MDI. So this map is made with the same data from the CDC. It's the arsenic values by town, the maximum. Again, the same color scheme. The dark red is very high, and the yellow is below the limit. So like this box was below the limit. And you can see here in Blue Hill, northern MDI, you know, there are some high maximum levels, like in the hundreds of parts per billion. I've also included on this map, you can just sort of see the landscape behind the colors, and these black lines. Any guesses what those black lines are? It's a geological feature. Faults, yes, good. So these black lines are places where rocks, when they feel stress, they, like we do, but they crack when they feel stress, and there's an earthquake, and you get a permanent rupture mark, a permanent fault. And over many, many earthquake cycles, they become a long-lasting feature. And so here's the Noren Vega fault system that I talked about before, but we also have a lot of other faults in this area, some of which you can only see exist for a little bit, and then they're not mapped anymore. And you know, we have a lot of what Dwayne Braun taught me to call lovingly biological infestation in this area. Trees, plants, water. I love it, I do. I just, you know, sometimes it's like gets in the way of the rocks a bit, but you know, what I did here is I did some connecting of the dots and looking, I'm trained as a geomorphologist, I read landscape, so sometimes the landscape can tell us where there might be a fault. So my theory is there's some unmapped faults here, and one of them I think goes right through the northern part of MDI, and that's why the elevations are low, sort of near the southern end of Northeast Creek. I think that, you know, and also there's some in southern MDI. There's many faults. But, so here's zooming in, I think there's some faults that go through here. These are actually mapped. This is where the ovens are, just nearby here. So there's a bunch of mapped faults right in that area. So we know it's kind of cracked up. Plus, any place you have water like this, like faults tend to be low-lying areas. So sometimes the places where there's water can tell us where there might be faults. So why do I care about faults? This is the next part of the story. So hydrothermal fluids leached elements from the metasedimentary rocks. Those fluids are moving around through cracks. The only reason that we can even suck water out of rocks to begin with is because our rocks are cracked. I mean, granite's not permeable. The only reason we can have wells in Maine is because they're cracked up because of tectonics. So these fluids are moving along the cracks, and they're hot and they're filled with elements, but at some point they cool down, the amount of oxygen changes, the pH changes, and those elements dissolved will precipitate out of the water and onto the fault plane that they're traveling along. So the idea is that these faults might serve to concentrate metals or elements that precipitate out of these fluids. A colleague of mine who teaches at Union College, John Garber, and has a house in Steuben, has dabbled a bit in with uranium oxides. He's very interested in radioactivity, and he found very high levels of uranium oxide minerals right along fault plains, but then low levels in the granite next to it. so these fault planes might concentrate some elements. And so that's why I thought that this area of northern MDI might be a good place to study, because there's a fault, and there's metasedimentary rocks, and there's granite. So to review what the rocks look like, here's MDI. These green and blue rocks are metasedimentary, that's the Ellsworth schist. These are the igneous rocks, the Cadillac granite. And these are the faults that I think might be there. So this area of MDI is a perfect study area to look at faults, and it actually might be a little too complicated, but it was a good target and a good place to start with this study. So I decided to just take a chance and go out and try to sample some wells in this area in order to see if there's a relationship between geological structures and rock type and groundwater quality. And I did this with students, many of them, and the All About Arsenic team. Thank you for letting us participate, and also over 150 volunteers, some of who are here tonight. Thank you for coming. So thanks for letting us sample the wells. So we went out and we sampled, here are the dots of generally where the wells are. They go up as far as this far north and this far south, so that we are well into the granite and well into the schist. And I'll just zoom in. These aren't the exact locations, and they're not even all of the locations. I haven't added some of the new ones yet, but we've sampled over 150 wells. So we took those data, all the data that we got for 14 different elements, and we made maps of the distribution of arsenic, say, or iron, or uranium. And we compared it to the bedrock. So here's the simplified bedrock, granite and schist, and here's where I think those faults are. And note that this map has no coastline, and it has no roads, and it has no information, so you can't really tell where people live. It's just granite and schist with a fault zone. And then here is, it's kind of a contour map or a heat map that Gabby made. She interpolated the value of arsenic between different well sites. We took the distribution of arsenic values in these different wells, and we made this heat map, and you can see that higher values are sort of located near this fault zone, maybe this inferred fault zone right here. And also higher in the Ellsworth schist compared to the granite. Granite has low, and I should tell you the scales. Green to orange is low. Orange is the EPA limit, which is 10. And then anything more red than orange, so orange, red to white, is all higher than the EPA limit of 10 parts per billion. So the granite is lower than generally, not everywhere. In fact, there's a fairly high level in the middle of the granite, so who knows. But you can see that there's sort of a rough correlation here. Now, if we look at uranium, we see exactly opposite. The scale is the same in that the greens are the low, I should stand here, I just thought of that, I'm sorry, now I'm lucky, half and half. So the greens are lower levels, and the reds are higher levels, so in the granite, there's high uranium. Uranium itself, at very high levels it can be a problem, but it's not so much the uranium we worry about, it's the radon. So radon is a gas that is produced by the radioactive decay of uranium. And a lot of people have heard about radon because they have mitigation systems for the air in their basement. And that was kind of something that happened in the 80s, I think. But it's also something that might be in the water. So you really should consider testing radon in your water. And after I bought a house on granite, and I couldn't help it. I had to test for radon, and even the inspector was like, "We don't usually do this." And I'm like, "I know, I want you to." And so I installed a bubbler in my house. But you know what? I feel like I can sleep at night. I take a shower and it's relaxing instead of thinking about the radon I'm breathing in. So it's not personal. The rocks are just where they are, and there's something to worry about either way. This is just iron. People always ask me about iron, and iron kind of tends to come and go. I feel like that concentrations can change through time. So I'm just going to show those few, but we have made maps for more of them. These two are the ones that I think are most of interest for public health in this area. So coming out of this study, we wanted to just look at spatial patterns, but we learned, 150 samples, we learned a lot of things. Like, some people have a filter on their well for arsenic because they know they have arsenic and they don't want to drink it. And so they have a filter. So here are 5 wells, and these are the arsenic levels in parts per billion, or micrograms per liter. Here's the limit, 10. And we sampled anybody who said they have an arsenic filter, we sampled before and after. And what you can see is This, with no filter, this sample had over 40 parts per billion, and the filter was functioning to take out a lot of arsenic, but it was still above the limit of 10. Here, a little bit of arsenic, and the filter successfully took all of it out. Here, there's a high, and it took most of it out to below the limit. Also with this one. In this one, well, the filter added arsenic to the water. But, that can happen depending on the age of the filter or how well it's maintained. And maybe there's even something chemically happening to interfere with how the filter works. We don't know. So I don't know. I certainly don't know. I'm a geologist. But this came out of the data, and I feel like it leads to more questions that we might ask and design sampling events around so that we can help people mitigate their problems with water. So these are just some of the questions that came up from this data, like the filter question. How do these quantities of arsenic and uranium vary in shallow wells, like dug wells? All those maps I showed you were just made from drilled wells, but some people have dug wells. How do private well owners even use the data when we give it back to them? And what are some of the barriers to mitigation, like cost, or what is it? And then also, are there seasonal changes in the abundances of arsenic and other things? And so this is one I put in blue because we're kind of getting going on that. We're going to start a seasonality study. And this is where I just wanted to quickly mention that, that other people have done this. There have been seasonality studies. All of these show that there are variations for different things, not just seasonality, but changes in flow because of the microbes sometimes. And I mean, there's lots of things that might cause little bits of variation in 3 different states, Minnesota, New Jersey, and New Hampshire. But I wanted to just say that I'm also involved in a project with Friends of Acadia and Brian Hinkle, the park, where we're monitoring watersheds on MDI. For the last few years, since the same time frame actually, 2016, where we're keeping track of the level of water in the stream, or the flow, how much water is available. So we have data from multiple watersheds on MDI that can tell us about seasonality on this island. And it's also a great other opportunity to have students be trained in water quality and questions related to our own community resource management. So here's just an example of some of our data. This is the Cromwell Brook in Bar Harbor at kind of higher flow here. And this graph is showing rain in these blue bars. That's precipitation through the summer months from starting April 1st through the end of October. And the water depth of the stream. So like how much water is in the stream. And you can see when it rains, the water level goes up and then it falls back down slowly. It goes up and then it falls back down slowly. And the stream, the water is flowing out to sea. Some of it might be seeping into the ground. But the main thing to get from this is that water levels are high in the fall when it's raining, and they're low in late August, early September. In fact, Cromwell Brook, Jordan Stream, a lot of these streams even run dry in the late summer. And some of the people whose wells I sampled told me their wells run dry in late August. So if their well is running dry, is there more, might the arsenic concentration be changing during that dry period of time? Yeah?
Just take a minute and go back to groundwater.
Sure.
How it's recharged. You think about it, the Earth is a sponge, and does it move through? There are some assumptions that need either validating or trash.
Yeah, you're right. So groundwater can move around on this island as fractures, or the cracks in the rocks, intersect. So the water is moving through these cracks under the ground. It's recharged when it rains and water can seep into cracks or move along a stream until it can seep into a crack back into the ground. And that's the groundwater I'm talking about in the bedrock that's hundreds of feet down. But there's also groundwater that's shallow that people might be drinking out of dug wells, shallow wells. And that's also recharged from rain, or even a lake or a body of water that acts as a reservoir could slowly leak into the groundwater. Certainly, if I show you well data that's connected to stream data, you'll see that the seasonality is the same. So that means that there's a connection between, the rainy season, or when it rains, the streams, and the groundwater. That tells us that the recharge is linked to the rain. Probably also snowmelt and the storage that's in these lakes. But yeah, that's a good question, and it's really hard. I don't really want to be involved in groundwater projects here because it's complicated. You can't see how these fractures intersect. Drillers use a camera that they stick down a well sometimes to try to see where they are, but It's so much easier in like Georgia and South Carolina where there's just sand and silt, and you can very easily model that groundwater. But, so does that answer your question, or do you have any?
Well, I'm in charge of stupid questions.
Okay,
So
no, that's okay.
Where does the groundwater go? In other words, why does it descend if you're already 300 feet below sea level?
Well, I mean, people are taking water out of the ground, and that groundwater is flowing, albeit quite slowly. My hydrology professor used to say to anybody who's late to class, "You're as slow as groundwater in the morning." And I was like, it's not even funny, but all these years later, I say it to my students. But, I mean, so groundwater is flowing, and it's flowing from, it's a pressure-driven flow. And it's kind of like elevation. It's called from high head to low head, but it's driven by pressure. It flows, and as more people draw the water out of wells, that can draw down the levels. And since it's flowing, if it doesn't rain for a while, then the water level is going to keep going down. People are drawing it out, and it's flowing away. So it does need to, to rain to recharge the groundwater. That's like the short version of it. But then there's complications with where it can seep in from lakes or other bodies of stored water. We're really lucky here. We have a lot of water. We really don't need to worry about, droughts and running out of water necessarily. But I do think it's worth worrying about how our water quality might change with seasonality, especially given things that might happen with climate change. I mean, maybe our rainy and dry seasons will get longer or shorter or more intense. So, I've probably talked for a very long time. I don't know whether I want to show you. There's one more really kind of cool thing. Let's see. The USGS keeps track of the water at Otter Creek, and you can really see the seasonality here at the stream level. High water, low water, high water, low water. And just in the last few years, it's been getting really low. So you can see in this, I just zoomed in, that's the wet season and the dry season, the wet season and the dry season, where the stream at Otter Creek is extremely low. The groundwater data is a little bit harder. On this plot, these green dots are well levels. So at McFarland Hill near the park, there's a well that's 500 feet deep. And these dots represent depth below the surface. So the higher the dot, the higher the water, the more water in the well. And the lower the dot, the lower the water in the well. So you can see that there's a dry season, and I highlighted them in brown, and a wet season, a dry season, a wet season, a dry season, a wet season. And you can also see that at the gauge that's at the Crooked Road, like right near the stone barn, there's a well there, and you can see very little changes, but wet season, dry season, wet season, dry season. And this is correlated with the rain. So this is all the rain values for the different years. So I did this because I wanted to see when is the dry season. And the dry season is, July to October, but really at the end of September, August to September, like end of August to the end of September is really dry. So I went out and sampled just 25 wells, like this just happened, some of you as well, I think I sampled some of your wells. I went out, I just called people and said, it's the dry season, I want to get another sample and compare it to the wet season. So we sampled 25 wells, here's a few of them, and the question was, does the arsenic value change noticeably? And for some of them, it makes a difference. Here, let's look at well O. Here's 10, the limit. If you sample that well in winter, you will not get a note back from the state saying your well is above the limit. But if you sample it, well, I don't know if this is going to hold for every winter or every wet season and dry season, but the two samples we have, it was well above. 18, 17. So maybe not, not hundreds, but then you'd get a note back from the state saying, your well has high levels of arsenic above the limit, you might want to mitigate. So it matters when you test the well. Most of our samples were collected during January and December, so the wet season. And I don't have students. I don't have the army of students in August and the beginning of September. They're just coming back. There's no way they're going to be able to come help me sample wells. So this summer we're going to make more of an effort to do that and go resample wells and hopefully start sampling the same few wells again and again to look for changes. And the grand hope is to be able to suggest to the state and people who make recommendations for people to maybe sample your well at different seasons, or maybe sample it in the dry season so you can see what is the worst potential. And I should say, we don't have a lot. These are just two samples, one in winter, one in the summer. We don't have a huge data set yet. So I just showed some 5% errors here that is more than the analytical uncertainty, but to be conservative, just to note that these are in fact different values. So the one well we measured had a difference of these are 250 parts per billion, it went up to over 700. I mean, that's like, you don't even want it exposing on your skin. So there are sometimes that it's kind of important to pay attention. What can be done? Well, there's lots of opportunities. One good mitigation opportunity is the pitcher filter. And so there's been a study through Dartmouth Lab that they tested all these different pitcher filters, you know, like Brita and et cetera. And they found that the zero water pitcher filter takes all the arsenic out, no matter what, if it's 10 parts per billion or 100 parts per billion. And also, oh sorry, this started, should be 1,000. This is 1,000, it went down to 0, either way. And the MDI high school students repeated this experiment and found the same thing. Yeah. So there are mitigation, like the zero water filter or buying bottled water is a quick fix, but it may be actually more cost effective in the long run to get an inline treatment system for a tap. So the take home message, the bedrock contributes arsenic, uranium, and other things to the water, and geologic structures like faults might concentrate those elements further. And it's not personal, it just is. But private well testing is the owner's responsibility. It is not covered under the Clean Water Act. We have to take care of our wells ourselves. And consider filter maintenance and seasonality, and also radon if you live on granite, like get it tested. MDI Biolab Community Lab has on their website, the allaboutarsenic.org and the Maine CDC both have examples for what you can do to mitigate and opportunities to, you know, find out more about it. So, okay, this is what's coming up. Questions?
The last couple of years here on the island, the neotropical migrants have been leaving in August and September en masse. So it gets very quiet during that dry period. So that's something we're seeing out in the real world too.
And you think it's because
with
it's dry?
plants and trees and other things.
Yeah, right.
But, well, could be related.
Yeah, I mean the last few years have been very dry. Like on that stream gauge, you can see that it's noticeably different than the prior years. Yeah, thanks.
You focused on seasonality in terms of water, groundwater. How about seasonality in terms of the wells themselves?
How do you
Three-quarters
mean?
of the wells up here only use 2 or 3 months of the year. Does the arsenic level in those wells, specific wells, change over time?
That's a good question. In fact, some of the studies that I saw while when I would try to find anything about varying concentrations, some of the studies in other states were focusing on pumping. Like if these people are pumping, or if you pump, when do you pump, or how time, is there variance after the well has been installed? Yes to all of those. In some situations you see variability based on like who's pumping the water, who's drawing it, because it changes what's available. It changes the flow regime. And I don't know enough about this. I feel like we need like an aqueous geochemist and a groundwater hydrologist who focuses on fractured bedrock. It just kind of fell into it because I saw this data. But yeah, it's a really good question. There's a lot of variability potential. I don't think though, I mean, I shouldn't say, who knows how many parts per billion. It might just be, within a few parts per billion. That's what we saw, except for that one well. Yeah.
Do you know if there is a correlation between the groundwater uranium and the gas radon?
That's another question on here. The people who I know, this just came up. One of my colleagues who had really high uranium in her water had not tested for radon ever, and I said, you might want to, and it was what really high. So now I thought like, well, what is the magic point where, if you have this much uranium, you probably have, and I don't know. I think probably that exists. I feel like I need to dig harder in the literature and ask the right, search questions in Web of Science or something like that. But that's another thing. And I would love it if people sent me their prior data. Like if you know the radon and I measured your uranium, please tell me. I would love to know. But probably it changes too. It's a gas, so who knows? Yeah.
Hi, Sarah.
Hi. Thanks for coming.
Yeah, of course. With consideration of the zero water filter, do you think that that's going to have to be an individually kind of funded mitigation measure, or with further research, could that be state funded?
No, that's a good question. There are programs to help people with their mitigation, and I don't know that much about it. There's a little information on the All About Arsenic page, and Jane might be able to speak more about it, but at least for zero water, that's kind of like you buy that, just like you buy Brita. They have a program where you can like get discount filters. I'm a member of Zero Water. Bruce Stanton gave a talk here during a science cafe, and he just stood up here and said, like, I don't drink anything that hasn't been through a filter. Oh, you're a toxicologist. I'm not going to either. So I don't know if it's necessary, but I do it. Yeah.
They're a great lecture.
Oh, thank you.
Two questions. First of all, is the arsenic that we find now still sloshing around from having been made hundreds of millions of years ago from when the plates were still smashing around? Or is it still coming out of rocks but at a slower rate?
Well, it's all just moving around. I mean, like, it's not like we're, the arsenic maybe started in those rocks, but they had a backstory. They used to be on some other rocks and got eroded and deposited. So then they were in those rocks, and then they got leached out of them in the water, put on the, maybe precipitated into minerals, re-dissolved. So it's like kind of constant, you know, the salt in the ocean water that ends up in a tide pool that dries up on a sunny day. You get some salt crystals, and then when high tide comes, it redissolves. And so, I mean, it's just moving around. These elements can move around. So I don't know that we would ever know that. Although people have done some work with isotopes of arsenic to try to figure out, you know, is this arsenic that's coming from some of those chemicals, or is this from the bedrock? And if it's coming from the bedrock, is it because of pH, or is it because of the oxygen, or is it because of carbonate? I mean, so there's different chemical reactions that mobilize the arsenic, but I don't know that we're ever going to know, like, you know, its exact pathway. It's moving around. Yeah.
What's the chemical form of the arsenic?
So there are a few different ones, and I can't speak to this very, I don't know if Jane, you can, but
I think it's +3 and +5.
that's about all I know, though. I mean, it's just in the water as +3 and +5, and that's it. But I couldn't tell you, like, where it started in what arsenate, or what kind of, you know, arsenopyrite or what mineral, and then became arsenic 3 or arsenic 5. But I do need to know more about that.
Those are the two species that you'll find, and when we test, we're looking at those.
Right, and and it would be, I don't know whether you would expect more of one or the other for certain types of rocks or not, but both are included in the test as a total. Yeah.
I live in this area, and when I first moved here, I had such an enormous amount of manganese in the water. You haven't mentioned manganese.
Yeah, thank you. Yeah, I know. I already talked too long, so I was like, what should I take out? But manganese is another one that we see. In fact, that one well that had the largest change in arsenic had an even higher change in manganese, a much larger. In fact, it was exactly opposite the arsenic. It was higher in the wet season and lower in the dry season. So we do see changes in manganese in wells around the island as well. And I'm not sure the level of concern we should have around that. And I don't know if you know any more about that, Jane, manganese. But it is something that's come up, and people have asked about their wells. And some people have filters to take out the manganese, and I think it has more to do with taste and odor and things like this.
Well, it's staining.
Staining, yep.
Have you given this program to Poland spring water?
No. I have not. I've given this talk to the workshops associated with the grant, so to some teachers and participants in that group, and at Colby College, and to a biochemistry of food class, also at Colby College. So just around a bit, but no, I haven't, and I don't really think I want to do that. Yeah.
Should.
Well, yeah. This was really focused on MDI. Yeah.
So a comment and a question. One is that arsenic filters are very expensive when you're filtering a household.
A whole house.
And so I don't think it's fair to blame or to infer that people that don't treat it are not wanting to, but it's just
right.
It's very expensive. And the question is, so we're one of the wells that's been tested. Do we get to see the data and see how it compares to the
Yes. So you should be able to use the magnet and the number to go on, and we just got it back. So the most recent data, I don't know that you can see that yet, but the last few iterations you can, and I can send you an email about how to do that again. And the numbers that are associated with your samples. So yeah, and you're totally right. I mean, that's in that study that was like, what are the barriers? One of them is cost. And so for the low levels of arsenic, or for when you're not trying to treat a whole house, it's somewhat of a quick fix to get a filter, but a zero water filter, but that's still a cost. But yeah, the whole house systems can be a lot. And I think there's some programs to help, but maybe not enough programs. And that might be the next phase, advocacy. What should we do about this? Yeah.
Have you mapped the wells that have had shown a high incidence of arsenic in the area? I know that the data is anonymous, but have we put a general map of where these are to see if?
Yeah, those are the maps. So, I mean, not for the whole of MDI, but for the study area we made, that was the maps I showed that had sort of like the higher levels of arsenic were generally around the Ellsworth schist, and the lower levels were on the granite, but the higher levels of uranium were in the granite, and the lower levels of uranium were in the Ellsworth schist. So that's been done, but you can also sort of see that in the data from the CDC.
Because, well, I wanted to say this, the Connors Emerson tests that were done, there were a bunch that came out high in Bar Harbor. I live in Lemoyne, and we did a bunch there, which is Ellsworth schist, and we came out really low.
Yeah. I mean, it depends. Like there might be some people who have shallowish wells who are on Ellsworth schist, but their well is in glacial deposits. So there's some people whose well, even if the bedrock far down is Ellsworth schist, their well might just be sort of shallow. And I know there are a lot of glacial deposits around the Ellsworth area that even if you had 20, 40 feet or more, you might be in gravel, and so you wouldn't have an arsenic concern then necessarily. And also, I've sampled people's wells in arsenic, people's wells in Ellsworth schist that don't have any arsenic. So it's not always. It's just there are more there than in the granite. Yeah.
Quick question: Is arsenic more dangerous? Can you absorb it through the skin, or does it have to be ingested?
Well, I think at very high levels that it becomes a problem in the skin. And Jane, do you know?
Over 250, they recommend the whole house system.
Above 250, yeah.
So below that level, a drinking water filtration system
drinking water,
would
yeah.
be effective.
Mm-hmm. Yeah.
What do the towns do for their year-round water systems, and what are the arsenic levels present in the different town waters?
The towns around here are mostly on surface water. They're not pumping water out of the ground. The Eagle Lake is this water source for Bar Harbor, and there's multiple lakes on this island are water sources for the town. And so there are some treatment to those water, like there's a UV treatment system in Bar Harbor. Sometimes chlorine is used, but they don't, because it's surface water. There's not the same issue with arsenic. There's more of an issue to worry about, like with bacteria in surface water. So it's really nice to have so much surface water available here. It'd be great if the water systems went further than they do to serve more people, so we didn't have to have wells. But that's the thing. So I don't know. There are some towns in the New England area that are pumping water out of the ground, and they have to treat. And I'm not sure how they do it. I don't know. I haven't read much about it since we're on surface water. Yeah.
Would you expect, like, if you go further into Ellsworth and Trenton, would you expect the levels to be higher there just because they're surrounded more by Ellsworth, or is it more correlated with fractures?
I really don't know. I mean, I think that there are some little hot spots that to me seem like it's because the arsenic has been concentrated along fractures or are nearer to igneous intrusions. But the truth is, like, how well do we know the bedrock that far down below the surface? We don't even know it that well everywhere on the surface here because of the glorious biological infestation. So, imagine even just 100 feet down, we don't know. I'd love to, another study, like go out with some drillers and just collect samples at what's coming out of the drill core. I did that with them in Bar Harbor once, and it was so cool. At 100 feet, all of a sudden the drill just punched through, like dropped, like I don't know, 5 to 10 feet down into the well, and water started flying out. And at 100 feet, between 100 and 110, it went through a big fracture, and it changed from, I guess, the Bar Harbor Formation to potentially granite, I don't know. And there were rounded stones coming out of the drill rig that were like rocks that were not the Bar Harbor Formation, were not the granite, they were glacial deposits. So they can migrate through these fractures, and it was this huge, and they know about it. They're like, oh yeah, we got this fracture network, it's gonna be great, like we just gotta get to 100 at this point. And so the drillers, they know all this, and they don't necessarily, like they're not sending that, they don't know the rock, they don't care about the rock type, they're looking for the fractures. So that's a whole other study. I need like a COA student to want to do a project. Follow the drillers. Yeah, good question. Yeah.
Do you know whether we're taking the iron out of our water in Town Hill? But does that also remove arsenic? You said the systems are.
I don't think an iron removal system will take out arsenic, but I did see that there are sometimes when, if you have an iron removal system and you're not changing the filter enough, that can build up and put arsenic into your water. I think that's what one of the, actually not the one that I showed in that well, but another one, that was the situation that they think that it was just building up on the filter because otherwise the arsenic levels weren't that high. So no, not necessarily. Filters do different things, and I don't really know about them all. Yeah.
You commented that there are seasonal changes. Are you looking at annual changes, and you expect to find annual changes?
You know, I think that, I don't know if there are seasonal changes yet. I mean, that's just like we want to look at that. And there have been some studies of annual changes, and people have seen that. It really depends on where you are on Earth, and I mean, what is the situation with groundwater recharge and the climate, and so it's not apparent that you can just take one study from somewhere and apply it to here. But you know, the state recommends you test every 3 to 5 years, so that suggests that there is some variability. Yeah.
Is there a relationship between pH and the arsenic?
We aren't measuring pH in this study, but some studies have found that there isn't, and I think some have found that there is, and I think a lot of it depends on what is the depth of the well, like how much, like a lot of things could affect pH. So you kind of have to, you know, talk only about wells that are at some depth or only in this rock type in order to really like tease that out. Yeah.
You get my conscience, because my first well was 120 feet. It was dry, so now I'm 450 feet.
Yeah.
So I've got 2 different waters, basically.
Oh, cool. So you have one that's 120 feet and it would run dry so that you went deeper?
I don't know. I suspected as the community developed, our water table went down. I suspect that.
Interesting.
Either that or a geological moment. With the, you get out there and all of a sudden the concrete under your feet is shaking.
Yeah.
You know the rock isn't quite steady.
You know, I was told by a colleague that their wells ran dry and they all of a sudden sinkholes opened up on their land during the earthquake swarm that happened here in 2006 and 2007. I wasn't here then, but that many people, according to this person, that their well would dry, but then also other people told them that their wells changed too. So I don't know, maybe there's some community lore that I should be collecting too, like what did your well do? What did your well do? Do you remember when that was? Yeah. Cool.
Well, why don't you join me in thanking Sarah for doing a few announcements about upcoming science cafes. I know I will be at the next one on February 10th because it's about the science of wine. And Ian Drummond will be here and with Scott Worcester from Sawyer Specialties to talk to you a little bit about the science behind winemaking and why you love the wines that you do.
Can I just suggest that we expect to be like standing room only, and that we're going to really ask that you RSVP so that Scott kind of has an idea, because there's going to be great tasting, and I believe that's going to be at the MCBI building.
We can accommodate more people than this
Yes,
over at MCBI,
absolutely.
which is the building right across the way. So that's where we'll meet then. And then coming up, there's going to be some more water-related talks. We have Susie Arnold here, who's been really leading the charge here in Maine, talking about ocean acidification and the effects of kelp farming and how that may help mitigate ocean acidification. I definitely want to be at that one. And then next up will be Nishad Jayansundara from the University of Maine, and he has been working with Sarah and with me and with Ian and with lots of people here at MDI BL interested in that interface between water quality and human disease. He's been looking at kidney disease in particular in Sri Lanka. That's where he is right now, doing some field work, and I think he has a lot to tell us about not just what's going on there, but how that relates to what's going on here in terms of how water quality can impact human health. So it goes on and on from there, but why don't, so the next talk, the kelp farming is March 9th, and then April 13th, the talk about Nishad's work. He's a former COA student student as well. So there's this huge big loop-de-doop of Nishad coming back here to talk to us all. So I hope to see you all coming back in the future sessions, future cafes, and I'm sure Sarah will hang around a few minutes to answer questions, and Amy still has a little bit of wine.
What was the date of the next one?